Once again, please join the Desmos activity. The link is in the chat. If you need the link again, please let me know. We'll start with a little bit of review here. So this first page we are on, all right, it is our checking of conditions page from the previous lesson, right? It says in chapter 8, we introduce 3 conditions that should be met before we construct a confidence interval for an unknown population proportion, random, 10% when sampling without replacement, and large counts. These same 3 conditions must be verified before carrying out a significance test. All right, so again, we have the random, 10% and large counts conditions. These 3 things must be checked before performing a significance test. All right, these 3 things are checked during the plan part of our 4-step process. All right after we state what we're going to do, the next thing is plan, which has to do with checking our conditions. All right. So now we're going to scoot forward. Oh, I don't want to do it that way. I want to do it this way. And we're going to scoot all the way to screen 7. All right, that is the one sample z-test for proportion. All right. This is part of our part of the 4-step process. This is part of the calculation that we're performing. The one sample z-test, it is our inference method. It allows us to take the data and put it in a way that I can make a conclusion about it. It gives me something to compare with. All right, we're going to choose an SRS of size n from a large population that contains an unknown proportion p of successes to test the hypothesis h naught such that p equals p naught. Compute the z statistic. Z equals p hat minus p divided by the square root of p naught times 1 minus p naught divided by n. All right. We then find the p-value by calculating the probability of getting a z statistic this large or larger in the direction specified by the alternative hypothesis h sub a. All right. We find the p-value by using the z statistic we just found, like a z-score, and finding that on table A, and we get a proportion. Right? Remember, table A only provides us proportions less than a certain z-score. Right? So we have to use that complement rule if we're looking for the greater than proportion. Right? Or we can use symmetry, another option. Then we have here at the bottom, right, if our alternative is that p is greater than the null hypothesis, right, we're looking for the proportion under the curve greater than z. If we're less than, we're looking for proportion less than z. If we're just not equal to, we use symmetry and we find the proportion either greater than the positive value of z or less than the negative value of z and double it. Right, we have symmetry in this. Is there any questions about the first couple things we're reviewing here, conditions or this one sample z-test for proportion? All right, so we're going to move forward all the way up to screen 11. Now, obviously, you do have access to every screen in between 3 and 11 right now. You're welcome to be able to kind of peruse back and forth if you need to. But right now on the shared screen, we're looking at screen 11, the 4-step process for performing a significance test. All right, to perform a significance test, we state hypotheses, check conditions, calculate a test statistic and p-value, and draw a conclusion in the context of the problem. 4-step process is ideal for organizing our work. Essentially, we always should be using that 4-step process, right, when we're asked to test our hypothesis, right? So this is the 4-step process for significance tests. This has to do with proportions or means. So we'll use the same 4-step process in section 9.3. All right, state what hypotheses do you want to test and at what significance level? All right. Define any parameters you use. Plan. Choose the appropriate inference method. Check conditions. If the conditions are met, perform calculations. Compute the test statistic. Then you use the test statistic to find the p-value. Lastly, we conclude. Make a decision about the hypotheses in the context of the problem. Okay. This is our 4-step process. We should always go through all 4 of these steps when solving a problem. Okay. And in a nutshell, these are kind of the biggest things we need to take away from this section as far as notes are concerned and like processes. There's other little bits and pieces like along the way, obviously that's within between screens 3 and 11 here. But these are the big nuggets. All right. So first, we're going to look at screen 12. This is a 4-step process practice problem having to do with population, proportions, and performing a test. Right. A drug manufacturer claims that less than 10% of patients who take its new drug for treating Alzheimer's disease will experience nausea. To test this claim, researchers conduct an experiment. They give the new drug to a random sample of 300 out of 5,000 Alzheimer's patients whose families have given informed consent for the patients to participate in the study. In all, 25 of the subjects experienced nausea. Use the data to perform a test of the drug manufacturer's claim at the alpha equals 0.05 significance level. You have a link to our formula sheet and tables, right? Because we will use table A. Okay. I recommend doing your work on paper and then uploading a picture of your work using the upload image option in the bottom left corner here of the text entry box. You can also just type in your work if you like. And so here's our problem. Is there any questions about this problem and what you're being asked to do? And we're going to talk about this. I saw a lot of really good work. I left some of you guys some comments on your submissions. Remember, right now we're practicing, right? It's very important to kind of be strict with yourself and practice all the parts. It's really good if you're able to do all the calculations and identify all the proper values, right? That's a really excellent place to be. The next step is making sure that you're doing things in a very, for lack of a better word, an eloquent way, right? That you're putting things in that 4-step process and you're writing things down, using full sentences and complete sentences to set things up properly. And that your conclusion is ultimately tied back to the original context. It's not just saying we don't have evidence for the claim. It's restating essentially what the claim was or how the evidence does or does not support it and what the ultimate conclusion is. Right, so we'll see some example of that right now. Excuse me. So I do recommend that you guys look at the shared screen if you're not doing that already. And I'm going to pull up OneNote that has the stuff on there that I want. And here we go. So this is the work and the 4-step process that I did in solving this problem. At the very top here, right, this stuff that I have here at the top is not part of the 4-step process. This is just values that I'm going to need. All right. This is like preliminary. This is what I did before starting my 4-step process. I identified my hypotheses, my null hypothesis and alternative. All right, my sample size N, which was 300. In this case, I actually know the population size that I'm sampling from, 5,000. right? My sample proportion, 25 out of 300, which is 0.083, rounded, right? It is 0.08333333333 forever. And then my significance level, alpha, is 0.05. Right? This is all the like numbers, variables, values that I can pull from the context. Right? And for me, with getting organized, these are things that I want to have easy access to. I don't want to have to read back through the context to get these numbers. Right? And so then we state, this is a step 1, right? We want to perform a significance test on the hypotheses H not such that P equals 0.1 versus the alternative hypothesis such that P is less than 0.1. Right, we're interested in what our researchers want to find evidence for is that there's less than 10% of the people who take this Alzheimer's drug will get nausea. Right, it's going to help them sell their drug. Right, where P is the true proportion of the 5,000 Alzheimer's patients who would experience nausea while taking the drug, right, at an alpha equals 0.05 significance level. Okay, so this is all step 1 of our 4-step process. We're stating what we're going to do. We give the hypotheses, right? I've stated parameters and what they mean and what the significance level is that I'm using. Next, we go to step 2, plan. If conditions are met, we will do a 1-sample z-test for the population proportion P. So again, I'm kind of putting this phrase in here, if conditions are met, right? Which means like, this is what I want to do if things work out. So we're going to do a 1-sample z-test. Right, the 1-sample z-test, that is the inference method. Right, part of the planning stage is saying what method you will use. In this case, we're using the 1-sample z-test for the population proportion P. We then check our conditions, right? Random, the sample was chosen randomly. We were told that in the context, so we're good there. 10% condition, 300 divided by 5,000 is equal to 0.06, which is less than 0.1, right? So 10% condition is satisfied. Lastly, the large counts condition, 0.1 times 300 is 30, which is greater than 10, and 0.9 times 300 is 270, which is greater than or equal to 10. Large counts is satisfied, we're good to go. All right. So the planning step is done. So now we do the math. We do our calculations. All right. We find the test statistic, that is Z. Right. And that's our formula, P hat minus P divided by the square root of P naught times 1 minus P naught divided by N, right? And we're replacing, we're substituting all of these variables with the values that I listed up at the top of my work. Get 0.083 minus 0.1 divided by the square root of 0.1 times 0.9 divided by 300. All of this work right here, the 0.1 times 0.9 divided by 300, all of that is under the square root sign. Please be careful with that. If you're putting this in your calculator, make sure to put parentheses around that once you start your square root to make sure that your calculator knows all of this is under the square root. Right? And then we get negative 0.98 approximately. All right, and again, this is if you used 0.0833. Right, if you kept more decimal places, you'll probably get a slightly different decimal as the result. However, it should still be negative. It should be pretty close to this value. Right, then, right, this is our p-value here. And this is the other part of do, right? Calculate the test statistic, find the p-value. So this is the other part of the calculation steps. Our p-value is equal to p, the probability of z being less than negative 0.98. which is approximately 0.1635. This is from table A. All right. Our p-value is greater than 0.05, so therefore we failed to reject the null hypothesis. This right here is not a conclusion. That is just work for me as part of my calculation steps that ties it together so now I can write the conclusion. I'm just saying what this p-value means since it's greater than 0.05. It's kind of like scratch work. Now we're ready to write our conclusion, right? Because the p-value 0.1635 is greater than alpha equaling 0.05, we failed to reject the null hypothesis. We do not have convincing evidence that the proportion of these 5,000 Alzheimer's patients who would experience nausea while taking the new drug will be less than 10%. Right? I have provided the details that tie this back to the context. Right? If all you say is we do not have convincing evidence that the alternative hypothesis is true, you have not completely answered the question. You need to provide the details that connect this to the context of the question. All right. And so that's what's been provided in our conclusion. Is there anything I can clarify here? Any questions? The other thing we can do is we can use technology to help do the calculations. All right. So if you have your calculator, the way to do this calculation in your calculator is you're going to go to the stat function. Right? It's this kind of middle button right here. And we're going to go over to tests. Right, we'll click over twice. So now we're highlighted on tests here. We're going to do the one proportion z-test. It's the fifth option. Right, I've already filled this out with our data from this problem. Right, the null hypothesis is that the proportion is 0.1. We have 25 people in our sample that experienced nausea. That's the X is the number of people who got nausea in this case. Our sample size is 300. And we want to know if the proportion is less than the null hypothesis, right? That's our alternative. Right, so this is all the stuff we need to fill in. Now that that's filled in, we'll go to calculate. You can have it draw, and it should draw the like normal curve and show the shaded area. We can look at that later. So hit enter. And so this is the stuff that goes along with the proportion being less than 0.1. We get a z-score of negative 0.962250, blah, 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 blah. All right. Our p-value is 0.16796. Right. Notice that this p-value is slightly different than the one that I got. However, they're close enough, right? They're relatively close, and they both give us the same conclusion. All right, p hat 0.083333. That's the same p hat that we got here. And again, it tells us what our sample size was. But the main two things we're really curious about, right? The z statistic and the p-value are provided here. All right, so we can get those values using our calculator a little bit faster. It just could depend on whether or not the test is saying show how to do this calculation, use the the formula, or use the formula in table A or technology. You can use either one. If you're using technology, you need to explicitly say that you're using that function, the 1 proportion z-test on the calculator, and show that it's been like you're putting in the correct values for the variables. Okay. Is there any questions about the calculator? There we go. So the next, type 2 error in the power of a test. A significance test makes a type 2 error when it fails to reject a null hypothesis that really is false. All right, so a type 2 error is failing to reject the null hypothesis when the alternative should be true. All right, type 1 error is rejecting the null hypothesis when the alternative is false, right, or when the null is true. So there are many values of the parameter that make the alternative hypothesis true, so we concentrate on one value. There's an infinite number of possibilities, right? So we just pick one. The probability of making a type 2 error depends on several factors, including the actual value of the parameter. A high probability of a type 2 error for a specific alternative parameter value means that the test is not sensitive enough to usually detect that alternative. All right, so a high probability of type 2 error means that our test is not set up in such a way that we can detect if that alternative is actually true. All right. The power of a test against a specific alternative is the probability that the test will reject the null hypothesis at a chosen significance level alpha when the specified alternative value of the parameter is true. So essentially, it's the probability that we will correctly reject the null hypothesis when this particular value of the probability is the true value. We want a higher power because that means our test will more often correctly tell us to reject the null hypothesis. Okay, to help this make a little bit more sense, we have a video, one of the AP Daily videos. We're going to watch about 4 minutes of it. This should help make more sense than what probably I just said. All right, and I need to make sure that you guys can hear this. Go. All right, please let me know if you can't hear the video. I should have.
That will affect your choice in significance level. Now let's talk about power and type 2 errors. In many contexts, a type 2 error is more consequential. I say this because in most research, researchers are trying to show that the alternative is true. And if they make a type 2 error, that means they didn't find convincing evidence the alternative is true, when it really is. So their suspicions were correct, they just didn't get the data to back up their suspicions. So for a researcher, a type 2 error is really bad news. Well, they came up with a word to talk about the probability of avoiding a type 2 error, and that word is power. So power is the probability of avoiding a type 2 error. The power of a test, then, is the probability that a test will correctly reject a false null hypothesis. Notice it says correctly there. Power is describes a correct decision. So the null hypothesis is false, and our data suggests that it's false, gives us convincing evidence that it's false. So power is the probability that we find convincing evidence for the alternative when the alternative really is true. That means the probability of a type 2 error is 1 minus the power. Remember, if power is the probability we avoid a type 2 error, then 1 minus the power is the probability of a type 2 error. Now let's look at an example to put this in context. To investigate if high school students associate the color green with being more natural, 2 student researchers randomly selected 30 students from their school. Each student was asked to taste 2 cups of lemonade in random order and state which one tasted more natural. One of the cups was green and the other cup was white. And unknown to the taste testers was the fact that both cups contained the same brand of lemonade. From previous videos, remember that we talked about the null hypothesis being p equals 0.5 and the alternative p greater than 0.5, where p is the proportion of all students at this school who would choose the green cup. Now, suppose that researchers used a significance level of 0.05 and that the power of the test against an alternative of p equals 0.64 is 0.45. Interpret the power in context, then find the probability of a type 1 and a type 2 error. So before we answer these questions, I want to reread the question because that first sentence might sound a little confusing. It says, suppose that the researchers used a significance level of 0.05. Well, that's pretty standard. And that the power of the test against an alternative of p equals 0.64 is 0.45. So we're saying the power is 0.45, and it's that number for the specific case that the truth is 0.64. We're not going to get into the calculations in this video, but the calculation of power depends on what the true value is, if it's something different than the null. So in this case, we're assuming the true value is 0.64, and then we've done calculations to show that the power equals to 0.45. Again, you don't need to worry about where those numbers come from. I just want to make sure you understand what it's describing. So interpret the power in context, and then we'll find the probability of a type 1 and a type 2 error. So here's what the power means. If the true proportion of students who would choose the green cup is 0.64, then there's a 0.45 probability that we find convincing evidence that more than 50% of students would choose the green cup. In other words, there's a 45% chance that we'd find convincing evidence for the alternative hypothesis. Now, as far as the probabilities, the probability of a type 1 error is equal to the significance level. That's easy, 0.05. And the probability of a type 2 error is 1 minus the power. So remember, power is 0.45, and so the probability of a type 2 error is 1 minus 0.45, or 0.55. Now let's talk.
Alrighty. So hopefully that helped make a little more sense of this idea of power and type 2 errors. Again, you're not going to be expected to be able to calculate power or type 2 error at this point, but you should be able to interpret it and use one to find the other. So next, all right, the significance level of a test is the probability of reaching the wrong conclusion when the null hypothesis is true, type 1 error. The power of a test to detect a specific alternative is the probability of reaching the right conclusion when the alternative is true. All right, that's power. We can just as easily describe the test by giving the probability of making a type 2 error, sometimes called beta. All right, power and type 2 error, the power of a test against any alternative is 1 minus the probability of a type 2 error for that alternative. That is, power equals 1 minus beta. We also saw that the probability of a type 2 error is equal to 1 minus the power. They are complements of each other. Right. Then we have some basic ways that we can increase the power of a significance test, because essentially we want to have a nice high power if we can for a significance test, because that will allow us to, that gives us a better chance of finding evidence of the thing we're curious about, right? The alternative. Usually we want evidence of the alternative, right? As he was saying in the video. So a higher power gives us a better probability of finding evidence that the alternative hypothesis has support and to reject the null hypothesis. So we can do this, we can increase the power of a significance test by increasing the sample size, right? The larger sample size gives us more accuracy, and increasing the significance level. Right, so if we have a higher significance level, it gives us kind of a bigger target. We can also increase the difference between the null and alternative parameter values that is important to detect. This difference you usually have little to no control over. Usually the null and alternative parameters are just set for us in the question. Once they're set for us, we can't change them. Right? The only people that can change them are the people conducting the experiment or the people making it up. So usually we can't do anything about those. So we're going to typically rely on increasing the sample size and increasing the significance level. All right, so then we have one question here with a few parts. All right, and this refers back to the context from screen 12 with the Alzheimer's drug. All right, part A, describe a type 1 error and a type 2 error in this setting and explain the consequences of each, one possible consequence of each. The test has a power of 0.54 to detect that P equals 0.07. Explain what this means. And lastly, identify 2 ways to increase the power in part B. All right. So we can take 5 minutes here to come up with answers for these 3 questions. Again, if you need a reminder of what a type 1 and type 2 error are, those specifics should be in section 9.1 if you have notes for that. You can also just refer back to, I think screen 15 has a brief description of both of those in a way, right? So we'll do a few minutes here and then we will talk about this. All right, we're gonna talk about this. If you're still typing in your answer here, that's totally fine. Please continue, listen and follow along if you can. But we're gonna talk about the answers to this question. All right, so in this context, a type 1 error would be finding convincing evidence that less than 10% of patients would suffer nausea after using the drug, when in reality at least 10% would. So again, I'm not saying what a type 1 error is, I'm saying what a type 1 error would be in this context. Okay. A consequence of this would be the new drug is used in more patients, leading to excessive nausea. Right. A type 2 error in this context would be failing to find convincing evidence that less than 10% would suffer from nausea, when in reality less than 10% would. The new drug is used less, this is our consequence, even though it rarely causes nausea. Right? And ultimately that company loses money, right? So again, when you're asked these types of questions, make sure you're answering the question. It's not asking for define type 1 and type 2 error. It's saying what is a type 1 or type 2 error in this context. Right. Part B, if the true proportion of Alzheimer's patients who would experience nausea is really 0.07, there is a 50.54 probability that the result of the study would provide convincing evidence that the true proportion is less than 0.1. So again, the power, right, is the probability that we will correctly reject the null hypothesis if a given proportion is the actual proportion. So in this case, we're told that the true proportion is 0.07, right? And that the power at this value is 0.54, meaning if this is the true proportion, there's a 54% chance that we will find evidence supporting that the true proportion is less than 0.1. Okay. Lastly, part C, we can increase the sample size or increase the significance level, right, if we're looking to increase the power in this context. Right, we can't really change the null or alternative hypothesis. It's not in our means to do that. Is there any questions? Is there anything I can clarify about type 2 error and power? Okay. All right, so that is the last slide of this Desmos lesson for section 9.2. So I've taken off the restriction there. Real quick. So again, looking at our class here, guys, if we go into the modules, chapter 9 is almost entirely there. I'm just missing the activity for 9.3. There's lots of really good resources in here to help you guys practice and review the content for all the chapters, but specifically chapter 9, because that's what we're on. All right. The notes and resources has the study guide, right? I put in time and I type up a study guide for you guys. It kind of puts together all of the key concepts with examples and things like that. And there's also like video tutorials and different things such as calculator. We have our activities here. Also notice our assessments for chapter 9 are ready. You're welcome to take those or start those whenever you want. We will be starting section 9.3 tomorrow. And again, please take advantage of the practice problems and solutions. Those are opportunities for you guys to practice if you have time, which practicing this content is the best thing you can do to get a better, wrap your head around it. All right. And always, if there's any questions, please just email me. Send me a message on Teams, something, let me know. I'm more than happy to help. So there's that. Please don't forget about all the resources that are available on Canvas. Otherwise, if you have any questions or comments or anything you'd like to talk about within this lesson or previous lessons or other assessments, please feel free to stick around and talk to me about that. Otherwise, that is the end of the lesson. I hope you have a great rest of your day, and we'll see you tomorrow.